Hello everyone and welcome back to your YouTube channel and welcome to this amazing video today. As you must be aware, I have been recording this video related to electromechanical conversion systems. And a very fundamental concept when we are working with rotating machines is the way that we induce voltage or create forces and torque in magnetic configurations. So I have been explaining for many weeks the basic and the fundamentals to induce EMF, electromagnetic force, the mechanical force, and the torque. And today we have this video that looks extremely simple but is looking into the most important backgrounds of electromechanical conversions. In fact, this video is dedicated to calculating electromagnetic forces between parallel conductors. And I highly suggest that you pay attention to this video because these fundamentals, you will find this fundamental in many other places when we are working with electric machines, but also transformers or transmission lines, or even if you are working with substation bus bars. So without further delay, let's start by reading this statement over here. And let's consider two parallel conductors of negligible cross-section. That means that those conductors over here, there is not cross-section. And the total length of those parallel conductors is 0.25 meter long. Each conductor is carrying a direct current, in this case 10 amps. We identify the current on conductor 1 as I1 and I2 for the conductor number 2. Okay? What is important here that you understand is that we are using direct current because we want the magnitude to be constant over the time and equal to 10 amps. And also because this is direct current, the current direction will remain the same. So here there is the challenge. Determine the magnitude and direction of the electromagnetic force, F in newtons, between them when there are two cases over there. We will call this the case 1, we will call this the case 1, and this is the case 2. The case 1 is extremely simple because the conductors, there is a very small distance, 10 millimeters apart, and in this case the currents are moving in opposite direction. Here you can see the 3D representation. We have the two conductors over here. The distance of separation is basically D1, 10 millimeters. Be careful with the units. And you can see in red color those arrows defining the direction for the current I1 and the direction for the current I2. Case 2, you can see that we put apart a bit further the conductors. You can see here D2 will be 0.25 meters. And in this case, the currents are going in the same direction. You can see here the 3D representation, and you can see that both currents, I1 and I2, both of them are going in the same direction. So this is a very interesting problem and is related with the electromechanical force. So let's start the solution, okay? I already covered this topic a lot during the classes. I already defined this equation. And basically what you need to remember is that when we have two conductors, and they are having currents I1 and I2, and they are fully and totally in parallel to each other, the magnetic field created by these currents are affecting the other conductor. And as a consequence, we have a force interaction between the conductors. And the force between the conductors are defined by this very simple but very interesting equation over here. This equation is defining the magnitude of the interaction force. In this case, you can see that is divided by the total length of the conductor. But basically, the electromagnetic force per unit of length depend of mu0, that is basically the permeability of the free space, is a constant for pi 10 exponent minus 7. Here we have the current intensity on the conductor 1, the current intensity on conductor 2, and divide by 2 pi d, where d is the distance separating the conductors. So this equation is quite useful because will define for me the magnitude of the force. However, this is only magnitude, or this is a scalar formulation. So the main problem is that we use this equation and then we need to define the interactions, the direction of those interactions. So the direction of the force is basically defined by using the Hans rule. So there are two important hard rules that I already explained them very clearly during the classes. The first one that you must remember is the right-hand rule. The right-hand rule for a conductor, because there are several right-hand rules, remember there are several right-hand rules. But the right-hand rule basically, if you have a conductor, and in this conductor there is a current moving in this direction, so you can apply the right hand rule, and if this is the current direction, the remaining fingers will give you the direction of the magnetic field. So in other words, here we can see that the direction of the magnetic flux created by this current I1 is anti-clockwise, okay? So very simple, that is the right-hand rule. The right-hand rule will give you, for this case, the right-hand rule for a conductor will give you the direction of the magnetic field density. And the second rule that you must remember, and I already spent time explaining this during the classes, but also I explained this very well in the previous video, is related with the Fleming left-hand rule. The Fleming left-hand rules basically define the interaction between force, magnetic field density, and current. Is what we call the mnemonic FBI, okay? FBI is not related with the law enforcement institution in the US. It's basically force, magnetic field, and current. So if you remember, the Fleming left-hand rule basically say you use the thumb for the force, the index for the magnetic field density, and the current on the middle finger or the birdie, okay? So what it's telling you is that if we have magnetic field density and current in one plane, the the electromagnetic force will go perpendicular to that plane, and that will be the force, okay? So now it's time to understand what we are talking about, but using the example that we are talking about right now, okay? Right now we have the conductors, the separation between them, the distance that separate them is D1 and is 10 millimeters. Remember, be careful with the units. And as you can see over here, the current I1 is moving in this direction and the current I2 is moving on the other direction. That is basically the 3D model, but now we can have the cross-section representation. And if we look over here, the current I1, this is the current I1. The current I1 is creating this magnetic field. But at this very specific location, the magnetic field big 1 is going up. And when interacting with the current going into the paper, it's creating this amazing force F21. That is the force on the conductor 2 created by the current I1. Similar situation is happening with the other conductor. The current I2, this is the current I2 in red color, is going into the paper and is creating this magnetic flux density P2. And at this position here, the magnetic flux density B2 is going up. So now the interaction between this magnetic flux density B2 and the current 1 create this force that is going to the left by the left-hand rule of Fleming's. You can see over here, this is the F12, where F12 means the force on the conductor 1 created by the current I2. So in general sense, you can see that the currents, if they are moving in opposite directions, they are inducing those forces that they are equal in magnitude, but they are in different directions separating the conductors. So now the job is to calculate, basically to calculate the value of that very specific force. And to do that, what we need to do is use the equation that we already presented before. And you must remember this equation. This is the force per unit of length. You must remember that the separation is given in millimeter. So we need to convert into meters because we need to use the MKS system. So then is a very simple substitution. You can see over here, mu sub 0, I1, I2, do 2 pi d. So remember, this is mu sub 0, and mu sub 0 is 4 pi 10 exponent minus 7. You can see that pi with pi cancel, 4 cancel with 2, and there is a number 2 over here, and then we multiply by the currents and divide by the separation. So the first result that I am showing here is basically the force that you will experience with those conductors, but this force over here is basically the force in per meters. But in this case, we know that the total length of the conductor is 0.25, so we obtain here that the force in 0.25 meter is 0.5 exponent minus 3 Newton. So this is the answer. This is the answer for this first question, the question A. So the second part of the problem is also quite interesting because right now we have the same situation, but now we are changing the separation. The separation will be only 0.25 meters. And now also the situation changed because now we are considering the currents going, both of them at the same direction. And you can see the red arrows representing the currents, and this current I1 and I2, both of them are going in the same direction. So you can see now in the plane the direction for the interactions, okay? So you can see over here, let's start with the current I1. This is the current I1 is creating the magnetic flux density going anti-clockwise. And at this position, we have here the magnetic flux density P1. And when interacting with this current, and this is the current I2, remember this is the current I2. So in red color, the interaction between the magnetic flux density and the current create a force, sorry, that is attracting to the conductor number 1. Sorry. So let's repeat again for the second force. We have the current I2, and the current I2 is creating this magnetic flux density over here. And let's see, is going up, is creating this magnetic flux density. And in this case, the magnetic flux density is going into this direction I2. And the force over here, you can see that the forces, they are attracting each other. So in this case, you can see that, in this case, this is the direction for V2. So this is the direction for the magnetic flux density here. The interaction between the current and the magnetic flux density create attractive force. F21 represents the force on the conductor 2 created by the current 1, and F12 represents the force in conductor 1 created by the current 2. So now calculating the currents is very simple. It's just a basic numerical substitution. We are using the same equation that we already presented before, mu sub 0 I1 I2 divided by 2 pi d. So the force per length is basically 4 pi exponent minus 7, 10 multiplied by 10 divided by 2 pi 0.25. Remember, this is the separation that is a data given in the problem. So after the numerical substitution, we obtain that the magnitude of the force, in this case, the force 1, 2 is equal to the force 2, 1. They are identical in terms of the magnitude, and in this case, that force is per unit of length, in this case, meters. And the final step is that we care is about the force created by only 0.25 meter. So what we need to do is basically multiply by the total length, and we obtain over here that the force is 1.25 exponent minus 3 newtons. And in this case, the force is attracting each other or pushing each other, those conductors. So to conclude here, this is a very basic but very important example. Because as you can see over here, the direction of those currents, they define the direction of the force interaction. And in some cases, you can create attraction, and in other cases, you can create repulsion. So these basic principles, you will find those very basic principles when we are working with generators and motors, and you will find these in many other places, like transmission lines or transformers, or even substation bus bars. Something that is very important is that the basic principle that we are using here is also used in the future for some other courses. For instance, if you are sizing a substation bus bar, the substation bus bar, they must have the robustness in order to support, to survive to the mechanical stresses created by the short circuit currents. So in those cases, the study that we need to conduct must be very similar to this very basic background that we are showing here. So in general sense, just to summarize, this is the equation that we will use to determine the magnitude of the magnetic forces interaction. And we need to take into consideration the right-hand rule and also the Fleming's left-hand rule to do the calculation. So I hope that you understand the very basic explanation that I run here, and I hope that you learn how to calculate mechanical forces between conductors, parallel conductors carrying currents. And I believe, I strongly believe that this will help you with the basic understanding in the future for electrical machines. Well, I wish that you enjoyed this explanation. If yes, please leave a comment or drop an email if you have any question. Or if you like so much of this, please subscribe to the YouTube channel. And it was a pleasure for me. It was a pleasure for me giving you this video. I hope you enjoy, and I will see you at the next one. And I need to say now, bye now.